students, welcome to this course on robotics and control theory and practice. This course is divided into two parts, each having 20 lectures. I will take the first part, which is about the fundamentals and mathematical concepts pertain to robot manipulators, biped robots and their control. The second part is about the practical applications and implementation aspects of robotics, which will be taken by Professor Felix. So, the content of this course is as given below. So, in this first 20 lectures, we will see about the coordinate frames, homogeneous transformations, differential transformation and velocity of a frame. So, here we will consider a coordinate frame x, y, z and the origin. So, it is a fixed frame and another coordinate frame with x1, y1, z1 whose origin is called O1. So, we will consider how to represent the frame M, we call it as M frame. So, how to represent the frame M with respect to the frame F, its position and orientation. So, the position means how the origin O1 has shifted from the origin O, and the orientation represent how x1, y1, z1 axis are represented with respect to x, y, z axis. So, this will be represented in terms of the homogeneous transformation, which is denoted by F, T, M. T represent the transformation and F and M are the coordinate frames. So, this is read as the frame M with respect to frame F is denoted by a 4 by 4 matrix called the homogeneous transformation. So, this will be done, and the velocity of a frame with respect to another frame. So, if the frame M is moving in space with respect to the F frame, how to represent the velocity of the M frame with respect to F frame. And then the Dinawit-Hartenberg algorithm. So, this is with respect to a robot manipulator. So, this algorithm gives how coordinate frames can be fixed at each joint of a given robot manipulator, and the kinematics and inverse kinematics, trajectory planning, dynamics of robot manipulators and stability and control concepts and biped robots. So, this will be described during the course of the lectures. The last portion, application part, is from the lecture 21 to 40 will be taken by Professor Felix. So, the definition of a robot, broadly we can say that it is a machine which can perform a given task automatically using artificial intelligence and without human intervention. So, with in the place of human it can perform a task automatically. So, it is a machine with links and joints. We can say that broadly a robot manipulator is having various links and the joints at the connection of the links, and there is a hand or the end effector of the manipulator and a base, and it also will have actuators. Actuator is the motors attached at each joints, and sensors like position sensor, velocity sensor or the vision sensor like cameras etc. and a controller which using the computers, it can act as the brain of the robot manipulator. So, these broadly represent a robot, and robotics is a study on the design and analysis, selection of proper sensors and actuators and suitable control systems to perform a given task efficiently. So, this is the study of robotics. So, here the picture shows a humanoid robot, but a robot need not be in this particular shape. It can be a crane like a structure, or it can be insect like, or several types of robots which can perform any task automatically are all called a robot. So, here one particular robot is shown. So, it has a body and it has effectors, end effectors. So, there are here 2 hands are there and 2 legs. There are 4 end effectors are there for this particular robot manipulator. In this picture you have only one end effector and a base here, and then actuators at every joint, sensors like vision sensor or various other touch sensor etc. can be attached with a robot, and the controller which controls a robot to perform a particular task. So, this is with the mathematical analysis one can design various efficient controller to perform a task, and the software which will implement the controllers etc. So, a manipulator is the body of the robot. So, here we can see the body and excluding the end effector, the reference frame. So, to study a robot and control it, we need a reference frame. Coordinate frame has to be fixed first, and then within that coordinate frame all the movements of the robots are analyzed or controlled. So, here a coordinate frame is fixed here, that is a world coordinate frame, it is a fixed one, and the joint reference frames. If you fix various coordinate frames at various joints, then they will not be stable, they will be moving. So, the world frame is a fixed frame and the other joint frames are the moving frame of the robot. So, how to fix various coordinate frames at various joints is an algorithm that is called the DH algorithm, which will be studied in the coming lectures. So, degree of freedom is the number of variables which is required to identify the parts of a robot manipulator. So, the number of independent variables that should be specified in order to locate all the parts of a robot manipulator. So, we know that a rigid body will have 6 degrees of freedom, 3 position variables and 3 rotation variables, that is orientation variables. And a object moving in a plane, it has 3 degrees of freedom, because a 2-dimensional plane, if you have the position is represented by x, y, 2 variables are required, and the orientation of the object, if it is x, y plane, x, y axis, and this is x 1, y 1 axis. So, x 1, y 1 axis represent the orientation of this object with respect to the frame x y coordinate frame. So, here there are 3 degrees of freedom. So, x y is the origin has shifted from the original origin, and the coordinates frames x 1 y 1 with respect to x y. So, the 2 position variables and 1 rotation variable is representing the 3 degrees of freedom. And if we have more than 6 degrees of freedom for a robot manipulator, it is called a redundant robot manipulator, because to perform a particular task in space we need 6 degrees of freedom at the most, and more than 6 degrees of freedom, using that we can perform or reach a particular object in an infinite way. So, the such 7 degrees of freedom manipulators are called redundant robot manipulators. So, normally as there are infinitely many ways of doing the same job, the computing time for selecting an efficient way of doing will be huge, and normally it is not preferred in the industrial robots. And we can easily see that the human hand, it has 7 degrees of freedom and 3 degrees of freedom at the shoulder, and at elbow 2 degrees of freedom, and at the wrist 2 degrees of freedom. Of all of them are rotational movements only. Okay. So, the joints of the robot are of two types. One is the revolute joint, that is which makes a rotational motion. Another is the prismatic joint. So, prismatic joint is, so this represents a prismatic joint because it can, this joint is able to perform a straight line motion only. It will move forward and backward, and here the link will rotate like this. So, there is a axis of rotation which is perpendicular to the paper. Similarly, there is a axis of rotation perpendicular to the paper, and this joint also can rotate from its current position. So, these two are revolute joint. So, here it says that there is a revolute joint, and at each joint there is 1 degree of freedom. So, one rotation is available at each joint. So, at each joint it has 1 degree of freedom, and totally this picture has 2 degrees of freedom because there are 2 revolute joints, and here it is a spherical joint. So, it has a rotation in all the 3 directions, all the 3 perpendicular directions it can rotate. So, this is 3 degrees of freedom at a particular joint, and it is called the spherical joint. So, here we can see this is a revolute and prismatic motion. So, here the first one is called the prismatic joint. 3 prismatic joints are there. So, it is P 3 times, and it is called the Cartesian manipulator. And cylindrical, you have 1 revolute joint and 2 prismatic joint. So, it is cylindrical because the prismatic joint, one is, it will, this link will go up and down like this, and this link again it will move forward and backward, and one link is revolute, it will rotate here, the base is rotating. So, finally it can be seen that the end effector can reach points within a cylindrical shape of a solid. So, we can see that the height of the cylinder will be from the base to the total height, and it can rotate 360 degrees like this, and it can move forward and backward. So, in between 2 cylinders, whatever is the point available, the end effector can reach that particular point. So, it is cylindrical, and here spherical is 2 revolute joint, 1 prismatic joint. Here the, it can rotate like this, and then the last link is, it is a prismatic joint, it will go forward and backward, and there is a rotation of the second link, it will rotate in this particular manner. So, we can see that it will form a spherical type. So, here we can see that the base is rotating with the axis of rotation as the vertical line, and the first joint is rotating as the axis of rotation perpendicular to the paper, and the third joint is moving forward and backward. So, this will represent a spherical motion. You can see that the sphere will have the center at the joint, second joint, and radius is the total length of the second and third link. And here we have a revolute joint at the base and a revolute joint at this link and a prismatic joint which will make the link go upward and downwards. So, the end effector, normally we have to fix a coordinate frame which is given by the perpendicular vector which is called the approach vector, and if you connect the two fingers by a straight line, this direction is called the sliding vector, and the perpendicular to both sliding and approach vector is called the normal vector. So, this 3 is usually fixed at the end effector irrespective of what coordinate frames are fixed at various joints. So, for every robot manipulator at the end effector we have to fix a coordinate frame exactly in this particular manner. One is the approach vector, sliding vector and the normal vector in this particular order. So, the hand of the robot manipulator is also called the end effector, and it is of two types, gripper and tools. The gripper is a machine which has two fingers, for example like this, or it can be like a human fingers, or it can have simply the tool attached at the end effector at the end of the robot manipulator, that is also called a end effector here. So, in this video one can see a robot manipulator which is having links and joints and the end effector which grips which is having a gripper and takes an object placed here, and then it takes the object and then put it in a different place. So, the task of a robot manipulator is mostly picking and placing in a picking from one place and placing it in another place, or a task of a wheeled robot manipulator is taking an object and moving to a different place through wheels and then placing an object in a different place in a factory situation. So, similarly different types of robot manipulator. The task of a biped robot manipulator or a insect like or animal like with 4 legs and all. So, they are all utilized for different tasks in a factory situation or in an entertainment industry, etc. So, but most of the robots task is only to take an object and place it in another place, and the control design is mainly for planning a trajectory of the end effector, because it has to take from one place and place it to another. The intermediate path has to be planned properly, and how to control the robot for performing the particular trajectory. So, these are the main concerns of a study of a robot, study in robotics. So, here the terminology are like this. We have seen roughly about a robot manipulator, and the direct kinematics means how to write the position of the end effector with respect to the position of the base of a robot manipulator, the equation to be developed. So, that is using the DH algorithm, and the inverse kinematics, it represent how much a robot should, for performing a particular task, how much angles of rotation is required at each joint. So, the calculation of the angles of rotation at each joint for performing a particular task is called the inverse kinematics problem. And the trajectory planning is how to plan a trajectory for performing a particular task for the end effector, and differential motion represent the velocity aspects, with what speed the end effector should move, and the dynamics represent what amount of torque or force to be applied at each joint. So, the dynamic equation is nothing but the equation of motion of a robot manipulator or any rigid body. So, here we can calculate using the dynamics equation the torque or force to be applied at each joint for performing a given task. So, that calculation is called the robot control. So, this we will see in the due course. So, for a very simple robot manipulator, all these calculations are very easy. We do not require the DH algorithm or anything, just a simple geometry will give the kinematics equation and inverse kinematic solution, etc. So, here we see a simple 2-link robot manipulator, and it has 2 degrees of freedom. There is a revolute joint, first one x0, y0 is the base coordinate frame, and the angle theta 1 measured from the x0 axis to the first joint is theta 1, and if we extend the first link and measure the angle between the first link and second link, that is called theta 2. So, we can observe that from the x0 axis the link 2 is the angle between the x0 axis and link 2 is theta 1 plus theta 2. So, using this information and the information that the length of link 1 is L1 and link 2 is L2, we can easily get the equation connecting xy and the theta 1 and theta 2. So, that is very simple to see here. The point in x0 y0 space is L1 cos theta 1 is the x coordinate and L1 sin theta 1, this height is the y coordinate with respect to x0 y0 frame, and with respect to x1 y1 frame we can see that the position, the end effector position, x coordinate is L2 cos theta 2, the projection of this cos theta 1 plus theta 2, and the height is L2 cos of sin of theta 1 plus theta 2. So, now with respect to the origin O, we can see that the x coordinate is L1 cos theta 1 plus L2 cos of theta 1 plus theta 2. Similarly, the total height from the origin is L1 sin theta 1 plus L2 sin of theta 1 plus theta 2. So, that is shown here. So, with respect to the origin O, the xy coordinates are given by these two formula, and which is called the direct kinematics equation. So, we can write x is equal to L1 cos theta 1 plus L2 cos of theta 1 plus theta 2, and y is L1 sin theta 1 plus L2 sin of theta 1 plus theta 2. So, this is called the kinematics equation. Now, if theta 1 and theta 2 are given, it is easy to find x and y. So, that is called direct kinematics, and if x and y are given, find the value of theta 1 and theta 2, that is called the inverse kinematic solution of the problem. So, inverse kinematics can be easily solved by using simple manipulations, mathematical manipulations like squaring x and y. We call C1 as cos theta 1, C1 plus 2 means cos of theta 1 plus theta 2. Similarly for sine. So, if we square x and y, we get x square plus y square given by this expression. From that we can get theta 2 is cos inverse of this quantity. Because x and y are given, L1, L2 are already known to us, we can find the theta 2 value, and we can note that there are two values for this, plus or minus cos inverse of this quantity. Now, for each such value, we can get a value of theta 1 in the following way. So, we have x is equal to L1 cos theta 1 plus L2, by expanding cos of theta 1 plus theta 2 we get like this, and we want to find theta 1. So, we write x as cos theta 1 into this bracket minus sin theta 1 into this. We call them as A and B, because theta 2 is already found out, this bracket is known to us. So, we have x is equal to A cos theta 1 minus B sin theta 1. Similarly, y is equal to, we get B cos theta 1 plus A sin theta 1 is the expression where A is this bracket and B is this particular bracket, they are known to us. So, using this we can easily calculate by following this particular step, we get theta 1 as tan inverse of this quantity. So, here we should observe that the tan inverse will have several different values. So, if the numerator is positive and denominator is also positive, then it means the angle is in the first quadrant. It is like tan inverse y by x, some y by x. This y and this y are different, y and x is simply we are taking capital Y and capital X to denote the numerator and denominator. So, if capital Y and X are both are positive, the angle theta 1 which we will obtain is in the first quadrant, that is from 0 to 90. If capital Y is positive, X is negative, value. So, tan inverse of a negative quantity which we will get. So, this will give the angle as pi plus pi minus theta 1, where theta 1 is tan inverse, you can say mod y by mod x. We take the positive values of the numerator and denominator and find tan inverse, that will give an angle between 0 to 90. And so, pi minus that theta 1 value is, whenever the numerator is positive, denominator is negative, we get this value for theta 1. Similarly, for negative and negative, if both of them are negative, then we will get pi plus theta 1. Tan inverse negative by negative value is pi plus theta 1, where theta 1 is like this. And similarly for fourth quadrant, if y is negative and x is positive, we will get this is minus theta 1. So, tan inverse of x is positive, y is negative by positive, that is we will get minus of theta 1, where theta 1 is tan inverse mod y by mod x, this capital Y and capital X. So, depending on the numerator and denominator values of this expression, we can find the theta 1 values. So, we observe that for reaching a particular position, the theta 1 we can find like this after finding the theta 2 values. Theta 2 is having 2 different values. So, we can see that when theta 2 is positive, we get this configuration, and theta 2 is negative, we get the other configuration, because measuring theta 2 is from the extension of the first link. So, we can see that the link 1 is like this, and if you extend it from here, we measure the angle theta 2. So, this is in the anti-clockwise direction, which is called the positive direction. So, if theta 2 is positive, we get this configuration, and if theta 2 is negative, we get the other configuration. So, for reaching a same position x y, we have 2 solutions for the inverse kinematics problem. So, if we have several links, instead of 2 links, if you have more links, then we can see that there will be several solutions for reaching a particular position. So, in general, the inverse kinematic solution will be difficult if we have more complicated robot manipulators, and it is multi-valued, because to reach a particular position and orientation we can get several solutions, and there may be singularities, because if you give a particular xy value, the end effector position, if it is such that the bracket, the value inside this bracket is more than 1, then cos inverse does not exist. So, it means that the position xy is outside the reach of the robot manipulator, or in some different types of robots, a particular position may not be the links cannot reach a particular position. So, such difficult positions are called the singularities of the robot manipulators. So, we can see that there may be discontinuities in the path, so which will be dealt in subsequent lectures. So, here we see that a planar robot manipulator with 3 arms. So, here the first link has length L1, second has L2, and third one has the length L3. So, the solution, the kinematics equation is similar to the previous one, 2 link manipulator. We can, if the end effector position is xy, we can write x as L1 cos theta 1, L2 cos theta 1 plus theta 2, L3 cos theta 1 plus theta 2 theta 3. So, theta 1 is measured from the x axis, theta 2 is measured from the extension of the first link to the second link, theta 3 is extension of second link to the third link. So, we get the direct kinematic equation like this. Now, if you want to reach a object, a position xy using this 3 arm manipulator, then there are infinitely many solutions for this, because there are 2 equations and we have to find 3 unknowns, theta 1, theta 2, theta 3. So, there are several solutions for the a particular end effector position. So, for example, we can, to reach this particular position, we have this solution, 2 solutions are available, and if you change the first link to this position, and this can be again reached by 2 other positions. So, like that, for each theta 1 value you will get 2 different solutions for link 2 and link 3. So, like that we can get infinitely many solutions for this one. Now, if you fix this theta 1 plus theta 2 plus theta 3, that means if you want to reach a particular position, we can say that, for example, this is our position xy. So, this angle is theta 1, this is theta 2 and the third one is theta 3. So, this particular angle, this is theta 1 plus theta 2 plus theta 3. So, if you fix this value, the sum of all the theta values, it means the xy position is approached via this particular orientation of the end effector. So, by specifying this value, we are specifying from which direction we should approach the point xy. So, for having that particular orientation, we have now 3 equation and we have to solve the 3 unknown values theta 1, theta 2, theta 3. This will have a unique solution and the solution can be obtained in the similar way as we have done in the previous. Because if you take, so if theta 1 plus theta 2 plus theta 3, if it is specified by this particular value, we can, so this is known to us. So, what we get is x minus L3 cos of theta 1 plus theta 2 plus theta 3, that is equal to L1 cos theta 1 plus L2 cos theta 1 plus theta 2. And similarly, here if you take y minus L3 sin of this theta 1 plus theta 3 is phi, it is equal to L1 sin theta 1 plus L2 sin theta 1 plus theta 2. Now, if we call the left hand side as some capital X and write the left hand side of the second equation as capital Y. So, it is exactly like the 2 link manipulator equation. So, given this capital X and capital Y, we can find the theta 1 and theta 2 value, and if you have a 3 link manipulator, the rotation, the first link will rotate with respect to the axis which is vertical line, the second link will rotate whose axis is perpendicular to the paper at a particular configuration. It has the axis of rotation parallel to the previous axis of rotation. So, there are 3 axes of rotation, and when the end effector is to reach a point x y z, so how to write the relation between x y z and the 3 angles theta 1, theta 2 and theta 3. So, that is the 3 axis manipulator. So, the picture is depicted here and this video shows the exactly the same robot manipulator. The second link is rotating with respect to the axis perpendicular to this paper, and the third link is rotating with respect to the axis parallel to the previous axis of rotation, and the base is rotating with respect to the axis which is vertical line. And after writing the equation, kinematics equation, we can solve the inverse kinematics equation as we did it for the 2 link manipulator. So, we can easily see that the theta 2 is given by cos inverse of this expression, and so the inverse kinematics of the previous. So, we see that the direct kinematic equation of this robot manipulator is given by the simple geometric relation as in the equation 1, 2, 3, that is x coordinate is L2 cos theta 2 plus L3 cos of theta 2 plus theta 3 multiplied by cos theta 1. So, that can be seen from this particular picture. If you project the xyz point to the xy plane, we get xy 0, and if you project that xy 0 point here, we get x 0 0. Similarly, we get here 0 y 0 as the coordinate of the projection on the y axis. Here we have the angle theta 1 and theta 2, theta 3 are described here. So, from this geometry we can easily write the equation as given here. X is equal to, given by this, y is equal to L2 cos theta 2 plus L3 cos theta 2 plus theta 3 into sin theta 1, and z coordinate is easily seen from the picture as this height is L1 from here to here, and this height is given by the 2 link manipulator from here to here as L2 sin theta 2 plus L3 sin theta 2 plus theta 3. So, the sum of this whole thing is given by this expression. So, this gives the direct kinematics equation. From here, by just squaring x square and y square, we will get a similar equation like the 2-arm manipulator, and we get the inverse kinematic solution. First we get theta 3 and then we can get the angle theta 2, and theta 1 can also be obtained directly. Theta 1 can be directly obtained by just taking dividing equation 2 by equation 1. We will get tan theta 1 is y by x. So, theta 1 can be obtained from this. So, this video shows that the YouTube video shows the exactly similar robot manipulator, where the base is rotating like this and the 2 links are rotating. The end effector is reaching a given particular point. So, in this lecture we have seen the simple configuration of robot manipulators with the 2 link and 3 link, and how to write the inverse kinematic solutions for them. And in the subsequent lectures we will see more complicated robot manipulators. Thank you.